Hi everyone, welcome back. So in the last lecture, we looked at the rectangular waveguide, and today we want to go a little bit further on waveguides. So this is lecture 22, and we'll discuss a new topic, which is related to waveguides, of course, called calculus of variations for arbitrary waveguide geometries. I should just say calculus of variations for waveguides. Okay, for electromagnetic waveguides, let's say. Okay, so what's the idea here, right? So if you recall in the last lecture, when we looked at the rectangular waveguide, we said that we can use separation of variables to find the eigenvalue, to find the propagation constant and the mode profile. But that's not always possible. So you can do that for a very limited number of waveguide geometries like cylindrical waveguides, rectangular waveguides, and that's pretty much it. Now, if I have an arbitrary waveguide cross section, how do I solve this problem? How do I find what the mode profile is and what the propagation constant is? And that is done numerically using the finite element method. Okay, so that's what we want to establish today. How do you actually do it numerically? And we will use what is known as the Ritz procedure, or we will develop what is the Rayleigh-Ritz procedure to calculate numerically the waveguide mode profile and the propagation constant. Okay, so in today's lecture, we'll look at the mathematics part of it, the mathematics side of it. So we'll prove several theorems or relations. And then based on these developments in this lecture, in the next lecture, we will look at how do you use it and how do you use finite element analysis to calculate those quantities numerically. Okay, so let's start from the standard transverse wave equation that the mode profile satisfies, AC squared psi equal to 0. Now I can rearrange this as del t squared psi equal to minus AC squared psi. And then this looks like an eigenvalue problem, right? So I have eigenvector, which is this psi function, right? This is my eigenvector. This is the eigenvalue. And this is the operator, right? The Laplacian operator. Okay, and of course, every function is also a vector, right? A function, say I have a function of one variable, and you can write all of these points as different points in a matrix or a vector, like a standard vector, which is this kind of ordered list, and it would be infinitely large, right? Because you have infinite number of points here. So all of these values can be coming here. And because it's an infinite dimensional vector, you have to be a little bit careful with the linear algebra of infinite dimensional vectors. But basically, it's the same thing. All the same relations of linear algebra apply even to functions. Okay? And that's the reason that sometimes these are called eigenfunctions. So hopefully you're familiar with linear algebra. It's one of the prerequisites for this class. But if you are, then it should be pretty straightforward development. Okay. So my claim now is that AC, which is the eigenvalue of this eigenvector equation, um, is nothing but the propagation constant, and it can be derived from psi. Yeah, and it's not surprising because you can usually, once you know the eigenvector, you can easily find the eigenvalue, right? That's the procedure of solving an eigenvalue equation. Find the eigenvector and then find the eigenvalue, right? So we're saying that once we know the eigenvector, eigenfunction, we can find Kc. So how do you actually do that? In this case, we will use Green's first identity, Gaussian psi mn, and we apply the Green's first identity on the same function twice, basically using the same function. Then we get psi mn del t square psi mn. ds is equal to contour integral over the aperture psi mn d psi mn dn dl. Right, so since this is for a PEC, whatever arbitrary cross-section waveguide for a PEC, the right-hand side must be 0 from the Dirichlet and Neumann boundary conditions, right? DBC or NBC. Okay, and this term here is minus kc square psi mn. And of course, from this you can write kc square as surface integral over the product of the gradients ds divided by surface integral over psi mn square ds. Try that again. Okay, there we go. So given that I know psi, which is the mode profile of the eigenfunction, I can put it into this equation, and that would give me kc squared. Okay, so this is a nice relationship, but what we really want is to be able to find psi as well. Right, given a cross-section, can I find psi? Okay, and to do that, we'll use this technique called calculus of variations or variational calculus. It's a very general calculus technique, and it's widely used in many, many different problems in physics and engineering. And today we'll use it to do exactly that, is to find psi, and then once you know psi, you know kc. Okay, so this uses a quantity called a functional. Okay, so we define a functional, and I'll explain what that is. Define a functional f of f, which is, let's say, n of f over d of f. So it's a product, it's a quotient of two functionals. The numerator functional n of f is this, ds, and the denominator functional is f squared ds. Okay. All right. So what exactly is a functional? Right. A functional is a functional f of f is a mapping between function and a real number. Okay. So essentially, it takes a function as an input and gives you a real number as an output. And there are many functionals that you can define it. You're pretty much familiar with this. So minus infinity to infinity, f of x dx, that's a functional. So definite integrals are basically functionals. You can also actually define, so this is another functional, f of x, delta of x dx, right? So this is essentially just f of 0, which is a real number, right? So it's a mapping between a function and a real number. Okay? So we've defined the functional to be this one. This is a specific functional, right? And it has the same exact form as this, right? So I take this functional. If I substitute psi instead of f, then I get back to this, right? So essentially f of psi is minus ks plus kc squared, right? Because when I put f equal to psi, then I get this equation, and that is equal to kc squared. Okay, so we've defined this functional, which is defining the functional now. Okay, now comes the main claim. So given this functional, the claim is that the function that minimizes this functional f is an eigenfunction. Of the wave equation. With eigenvalue AC squared. Okay, so let's try to understand this. Right, so I'm saying that I have this space of functions. So I'll call this S. This is the space of admissible functions. So what do I mean by admissible function? A function that is continuous and its first derivative is also continuous. And it has to be that has to be the case because I need to take gradients, right? So I need the function and its first derivative to be continuous. So mathematical terms, that function space belongs to C1. But don't worry about that. It's basically a set of functions that are continuous and differentiable. Right now, in this space of functions, I have many functions. Let's say I have some function f. Now my functional maps f to some point on the real line. Right, so it has some real value. Okay, now if I map every single function to points on the real line, so maybe that maps there, that maps there, that maps there, and these are all values on a real line, right? Then what I'm saying is that the function psi, which satisfies, so this one, the function that satisfies the wave equation, that thing maps to a minimum. Okay, so psi maps to a minimum. So let me repeat that. If I look at all of these functions in the space of admissible functions, they all map to different points on the real line or different real values, different numbers basically. And the function that maps to the minimum happens to be the function that satisfies the wave equation. And the value of this minimum happens to be kc squared. Okay, so the value of this minimum is kc squared. So that's obviously a real number, right? So all of this is just a claim. We haven't proven any of this, which we will prove. Okay, so this is the space of real numbers. That's what it's saying. Now, of course, there may be many functions in here because you have many modes, right? M1, M prime, and so on and so forth. They all map to different minima. So at the output space, you have different local minima, global minima, and so on. Every minimum corresponds to one mode. The global minimum, the smallest of all of them, corresponds to the fundamental mode, then the next one, then next one, and so on. All of that we'll prove now. So it's kind of a lengthy proof, but very interesting, a lot of insights, and really cool real analysis kind of mathematics, okay? So this is the general idea of calculus of variations, is that you have an expression which you know exists, and the idea is that if you generalize that to a kind of perturbation analysis, where essentially I have this equation, I perturb from this point, and it just so happens that the physical reality corresponds to the minima in that perturbed space. Okay, that's the general idea. So we had this minimum, we have this physical reality, which is coming from the physics. We consider a general case of functions, and we show that the special case, which corresponds to the physics, minimizes this kind of variational thing, variational quantity. Okay, and that just so happens to be how nature works in some sense. Okay, so let's actually prove these results. Good proof. It's a nice proof. One of my favorite proofs in this class, probably my favorite. All right. So we start by supposing psi1 minimizes f of f and has eigenvalue kc1. So I'm just labeling it as psi1, the minimum. So what does that mean? That means that psi1 satisfies del t square psi1 plus kc1 square psi1 equal to 0. Okay? Okay. So if we're starting with the assumption that psi1 satisfies or minimizes f, and f was nothing but n over f, right? So which means that n of psi1 divided by d of psi1, which is nothing but f of psi1, is equal to kc1 squared, right? That's the claim. So we're starting by saying that, okay, if psi1 is the right solution, then it satisfies this equation based on the claim that we make. So n of psi1 is equal to kc1 squared d of psi1. Now, if I pick another function g that is also admissible, and I perturb psi1 by this g, then it must be that this equation is true, right? Because n of psi1 plus delta g over d of psi1 plus delta g is some other real number which is greater than kc1 squared, right? Because kc1 squared was the minimum. And since it's greater than kc1 squared, I can take d to the other side and I get this relationship. Okay? All right, so we'll take a slight detour of trying to calculate what these values are, this one and this one, based on the definition of n. Right, so n of a given function f is surface integral del tf ds. Now, based on this, we can also define generalized n, have two functions as the input, and define that as surface integral del df dot del dg ds. Okay? So essentially, n of f is nothing but n of f comma f. All right, so then we can write n of f plus g as surface integral del t f plus g dot del t f plus g ds. A new page. This is nothing but, of course, gradient can be distributed. Del tf dot del tf plus del tg dot del tg plus 2 times del tf dot del tg. And the ds factors and so on, which I'm ignoring. So this is nothing but n of f plus n of g plus 2 times n of f comma g, based on our new definition of n. Okay? All right, so based on this, we have n of psi1 plus delta g. This closes, actually this doesn't close. Delta g is n of psi1 plus del square n of g, right? Because n of g is integral gradient g dot gradient g. So you get two factors of del that come out. Plus 2 del n of psi1 comma g. And we also have d of psi1 plus del g is equal to d of psi1 plus del square d of g plus 2 del d of psi1 comma g. Okay. Now I multiply the second equation with kc1 square and I subtract. Yeah, upon doing that, I'll get back this, right? or I can rewrite this as minus this greater than 0. So upon doing that, I get the left-hand side, right? Because that is n minus kc1 squared times this. Okay, implies that 2 delta. So the right-hand side is what I'm writing down. Delta n of psi 1 comma g minus AC1 square d of psi 1 comma g plus delta square n of g minus kc1 square d of g plus n of psi 1 minus kc1 square d of psi 1 d of psi 1 is equal to n of psi 1 plus delta g minus kc1 square d of psi 1 comma delta g. Okay, this is full term. Okay, so this term must be 0 because if you go back, we have this equation here, right? And the right-hand side is greater than 0, right? Which means that 2 delta n of psi 1 comma g minus kc1 square d of psi 1 comma g plus delta square n of g minus kc1 square d of g is greater than 0. Okay. Now the interesting thing here is that my claim that this whole thing must be 0. Right? This is the claim. So we want to prove that claim. This is where the nuance comes in, right, of the proof. Okay, so you can have two cases. So let me call this term, we'll call this term capital delta, and I'm saying that that's equal to 0. Okay, so how do you prove this? So let's assume delta is greater than 0. Okay, if delta is greater than 0, I can choose little delta to be less than 0 because little delta is arbitrary. It can be anything, right? And small enough. So the argument is this: if I make little delta very small, right, then delta square is positive always and much, much smaller than little delta. And for example, this 0.1 or minus 0.1, then this would be plus 0.01. If this was 10 minus 10 to the minus 5, this one becomes plus 10 to the minus 10. Right, so this becomes negligible basically compared to this term. Right, so essentially if this term is very large, you can make this very, 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 very small, such that this term is much smaller and positive, such that this whole term becomes much smaller than this whole term in magnitude. And you can always do that because delta can be made arbitrarily small, right? Under that condition, this term becomes negligible or 0, negligible, not 0, close to 0. And this term will always be negative, at least if this is positive and this is negative and very small, then this whole thing is negative. And since this term became negligible, this whole factor is less than 0, right? And that's not possible because we know it's greater than 0, right? And small enough such that left-hand side can be made negative. That's not possible. Or contradiction, right? Or I should say contradiction rather. Because we know it's supposed to be greater than 0 for any delta. The other case, if delta is less than 0, then I can choose little delta to be greater than 0 and small enough. Same thing. Right? Such that LHS is less than 0, which is another contradiction. Right? So if this term is less than 0, I pick this one to be greater than 0 and small enough such that again this becomes irrelevant and the product is less than 0, which is again a contradiction. Right? So if delta cannot be greater than 0, delta cannot be less than 0, the only thing left is for delta to be equal to 0. Right? Implies delta is equal to 0, which is what we wanted to prove. And so hopefully you see the kind of brilliance of that proof, which is that given that little delta is arbitrary, it can only satisfy this equation for all possible values of little delta if this becomes equal to 0. Okay? All right. It means that n of psi 1 comma g is equal to, or I should say minus kc1 square d of psi 1 comma g is equal to 0. So this is a very important and non-trivial result, right? Okay. So now we can expand n and t. Surface integral del t psi dot del t g ds minus kc1 square surface integral psi 1 g ds is equal to 0. And now I'll apply the Green's first identity to psi 1 and g. Implies surface integral gradient psi dot gradient g plus g Laplacian psi 1 ds is equal to contour integral g d psi 1 dn dl. Okay. Now I'll substitute this term and this term are equal, right? So I can substitute basically, instead of this, I can write this, right? I mean to say that I can substitute instead of this, I can substitute this quantity, right? Because this surface integral is equal to basically this. I can put that in there. Okay, when I do that, I end up with surface integral g of del t square psi 1 plus kc1 square psi 1 ds is equal to contour integral g d psi 1 dn dl. Okay. Okay. So now another claim is that the RHS is equal to 0. Yeah, that's not very hard to show. For Tn, that's trivial. Or I should say for Te, it's trivial, right? Because for Te, d psi over dn is equal to 0 from the Neumann boundary condition. Whereas for Tm, since I have an arbitrary choice for g, I will choose g to also be Tn. Right? So I'm looking for solutions where psi1 is a TM mode. I can also choose G to be TM. So I'm choosing G from an admissible space of all TM solutions. Okay. G is from TM space solutions, and I can choose that. I can choose G, right? And it's not unreasonable to say that since I'm looking for psi1 as a TM mode, G also comes from space of TM modes, right? Implies from the Dirichlet boundary condition, G equal to 0 on the contour. This is only true on the contour. Remember that. Which means the right-hand side went to 0. Okay. So implies that surface integral left-hand side is 0, which is the surface integral G psi1 plus kc1 square psi1 ds is equal to 0. Now, since G is arbitrary, G is arbitrary implies that this argument must be 0. Right? Since it's true for many G's or all G's, it can only be true if the argument is 0. And we've used that kind of argument before. This is exactly what we wanted to prove. So we've shown that if we take psi1 to be the function that minimizes the functional, it satisfies the wave equation with eigenvalue kc1 square. Okay, great. So we've shown this. We've shown how to basically get psi1 kc1 square. The way you get it is you take f of psi or you take the functional f of f and minimize it. So if you minimize this functional, the solution you get from that minimum is exactly the mode that propagates in that medium. And then we'll see how to do that using finite element pretty soon. But we also want to show that we can find other eigenvalues. And so we found psi1 and kc1. How do you find the other minima? Right? There are many other minima in this equation. So the way you find it is by utilizing the fact that psi1 is orthogonal to all the other modes. Okay. So to find other or higher order modes, we use orthogonality. Okay. So what does that mean? So I had this space of functions S. Now one of my functions in this is my psi1, right? So if psi1 satisfies the wave equation, then any scalar or any scaled value of psi1 will also satisfy the same wave equation, right? Because it's an eigenvector. All scaled values of an eigenvector are also eigenvectors with the same eigenvalue. That's what eigenvector means, right? So then I look for solutions in the space S1 where S1 is the orthogonal subspace to psi1, right? So given that, let's say I'm on the Cartesian coordinate system, if psi1 is along Z, this is my psi1, then the orthogonal subspace to psi1 or to Z is the xy plane. Right? Because I know all the other solutions or all the other modes have to lie in this plane because they all have to be orthogonal to psi1. Right? So now I'm going to set my set of admissible functions to be functions that lie in this plane. So this is very, it's the abstract notion of this plane. I'm just giving you an example of a orthogonal subspace in Cartesian coordinates, right? So this S1 is the orthogonal subspace to psi1, okay? Now from this subspace, I want to find solutions that satisfy or that minimize the functional. Okay. So in other words, I'm looking for functions f. So my new f is here, let's say, such that f satisfies this relationship, right? Such that f is already orthogonal to psi 1. And this is nothing but d of f comma psi 1 must be 0 based on the definition of d. Okay. So AC2 square is obtained by minimizing n of f over d of f under this constraint. Now, of course, Kc2 square is greater than Kc1 square because Kc1 square was the global minimum, whereas now we're looking for a minimum after obtaining Kc1 square, right? So it cannot be a global minimum. It has to be greater than Kc1 square. It'll still be a minimum. So Kc2 square is in fact a local minimum. Okay, so we want to show that basically a function psi2 is the eigenvector which satisfies the wave equation, an eigenfunction that satisfies the wave equation with a wave number or an eigenvalue Kc2 squared or Kc2. Okay, so we'll also prove this part. So again, we start with a small perturbation to psi2, some function g, and we know that it must be greater than Kc2 square d of psi2 plus del g, because of course Kc2 square was the minimum when you have psi2. So if you deviate from the minimum, it's not going to be minimum anymore, it's going to be greater than that. Okay. And we also know that d of psi 1 comma g is 0. Right? Since the space of functions now that are admissible is S1. Right? And d of psi 1 comma any function in this admissible space is 0 because they're all orthogonal to psi 1. Okay. So we let P belong to S such that G equal to P minus C of psi 1. Okay, what does this mean? So I had my psi 1. Maybe this was my psi 1. So this is just an abstract notion of the vector functions or the eigenfunction psi 1, which is a vector. And I know G is orthogonal to this. Maybe this is G, right? Because G is in the orthogonal subspace to psi 1. Okay? Now I pick a function P, some P. This is my P, such that P minus C times psi 1 is equal to G. Or you can write P as nothing but G plus C times psi 1. Okay. So it's not in the orthogonal subspace to psi 1. It has some projection onto psi 1. And that projection is precisely this C times psi 1. Okay, so G is P minus O. I wrote that down already. And what is the value of C? So I should rewrite this here. G equal to P minus C times psi 1, where C equal to D of psi 1 comma P divided by D of psi 1 comma psi 1, which is nothing but D of psi 1. And this is exactly just the projection. If I want to find what is the C, I project P onto psi 1 and I divide by the length of psi 1. Right? That's what this is doing. It's the inner product of psi 1 with P divided by the inner product of psi 1 with itself. Okay. So what is this called? This is the Gram-Schmidt procedure to build an orthogonal basis, right? And that's exactly what we are doing. We know the moles form an orthogonal basis and we're building them one by one. So you started with psi1, you picked another p, you removed the component of p that's along psi1, and that gave you an orthogonal basis. And that's exactly what we're doing here. Okay, moving on. Now that I have all of these relationships, I can replace G here with P minus C psi 1. I have N of psi 2 plus delta P minus delta C psi 1 is greater than Kc2 square P psi 2 plus delta P minus delta C psi 1. Okay. Now I go through the same procedure as I did before. I expand these out, right? And then once I expand them using the equations we used earlier, I can remove the coefficient of delta because delta is arbitrary, just like we did earlier, right? So expanding and setting coefficient of delta equal to 0, we get this. This is the coefficient of delta. So I'm skipping a couple of steps because we did that just now. B of psi 2 minus P minus C times N of psi 1 comma psi 2 minus AC2 square D of psi 1 comma psi 2 is equal to 0. So that's the coefficient of delta. Okay, but we can set a few more terms to 0. This term is 0 because we know psi 1 and psi 2 are orthogonal and D is just the inner product function. So that's 0. We also know that if I go back, we know that N psi 1, any function P minus Kc1 square D of psi 1 comma P is 0. And we established that in the very beginning. If you go back all the way, exactly here, psi 1 with any other function G is 0. And that's exactly this. So I can write this as this is equal to this, which means N of psi 1 comma psi 2 is Kc1 square D of psi 1 comma psi 2. But this is 0, which means this is also 0, which means this term is also 0. Okay, so we end up with just this, which is N of psi 2 comma P minus AC2 square D of psi 2 comma P is equal to 0. Okay, and this is exactly what we had here. We go back, exactly what we had here. And then from that, we just expanded N and D. We used the Green's first identity, set the right-hand side to 0. And then we said that from that, you get this equation. And then from this equation, because G is arbitrary, you can show that it satisfies the wave equation. Go through the same process again, because this is exactly the same thing. So Green's first identity and setting RHS equal to 0 implies that psi 2 satisfies the wave equation with Kc2 as its eigenvalue. Okay. So that completes the proof. And since this is Gram-Schmidt, you can keep continuing this process, right? You minimize the function. Once you minimize the function, you add an added constraint that the new function that minimizes that function must be orthogonal to the first one, and keep going to find all the higher order modes. Okay? All right. So this basically completes the proof of this calculus of variations. Next, we'll take a look at how to use it to find the modal distribution and the propagation constant, and that is called the Rayleigh-Ritz procedure. Okay, I'll just call it Rayleigh-Ritz method. There is another method to solve for solve the wave equation or any kind of differential equation using finite element, and that's called Galerkin's method. So both of these methods are essentially finite element methods. Here, FEM. So if you start from a variational principle, it's called the Rayleigh-Ritz method. If you start from a differential equation, it's called Galerkin's method. Okay, so we've established one variational principle. So if you go back and do a quick review, and this is the variational principle, right? So we start from this function, we minimize this. Another way to say that is that we find the solution of f, such that the derivative of f over the function space psi is 0. The function that gives you that equation, that satisfies that equation, is the wave function. Okay? All right, so that completes the kind of development of the variational process. In the next, so I want to divide this into two videos or two lectures, just because it becomes too much for just one of them. In the next lecture, we'll look at how to actually use this variational principle with the Rayleigh-Ritz procedure to find the modes of a waveguide, which is exactly what is done in a wave port. Okay, so that actually will show us how wave ports work. Right, so in HFSS, there's this thing called wave port, which can also provide an excitation. And this is the theoretical development behind wave ports. And we'll see in the next lecture how wave ports solve for the modes of a given waveguide. Okay, and then we'll actually open up HFSS and see it in HFSS as well. So that's the next couple of lectures. Okay, so we'll stop here. Not very long video, hopefully, but maybe it's a good place to stop. And if you have any questions, you can leave them in the comments. If not, I'll see you in the next one. Thank you.